Okay, so from the last week, we started to discuss the point cloud representation for the 3D and some of the ideas about how we can basically design some kind of the neural net encoder that can take the point cloud as the input. So last time we discussed the basic architecture, which is the point net, which is taking the 2D array of the XYZ coordinates as kind of the input. And then this is the architecture that can perform many different things, right? I mean, so this could be the architecture for the classification or some kind of segmentation or the many other things. So the characteristics of like those kind of tasks is that this is the case that we are predicting some kind of the some information for the entire shape, while this is the case that we are predicting some information for each of the single D point, right? And the main idea that we discussed last time is that how we are going to achieve some kind of the desired properties, like the permutation, the invariance, or the equivariance, and also how we can achieve the transformation, the invariance. So we discussed some kind of the bunch of the ideas for that. And the basic things in terms of achieving the permutation, the invariance, is like how we are going to define a symmetric function, right? So this was kind of like the one specific way that we are making some kind of the composition of the functions to make another symmetric function, right? So when the g is a symmetric function, by having another like the function h and the gamma here, we can composite those functions in this way to make another symmetric function. So this was basically the basic module in the point net. And then to achieve the transformation, the invariance, especially for the 3D rotation, the invariance, we also introduce the idea of the special transformer, which is basically automatically predicting some kind of the transformation in a way that hopefully all the input data would be aligned in the given this space. So this was kind of the basic idea for the transformation invariance. So this was the architecture that we discussed last time, basically having some kind of the sequence of the shared MLP. So someone asked the question last time about the meaning of like these like 64, 64. The meaning of like those number is basically that these two numbers basically indicate that we are having actually two layers here. And obviously the input dimension for each of the points at this point is basically 3, right? So the first layer of the NLP would be taking 3-dimensional vector as the input and outputting 64-dimensional the feature. And the next layer will be taking 64-dimensional the feature as the input, making another 64-dimensional kind of feature as the output. So 64 basically means that we are having the two layers here. And then we can have another, the T-net here, the special transformer. And then these three numbers means that we are having the another 3 layers. Taking 64-dimensional feature as the input, making another 64-dimensional feature, taking this as input, another 128, taking this input is like 124, right? I mean, this is like one specific way. We are just making a sequence of the shared MLP layers and having the max pooling here and taking another MLP, right? The same thing. And the idea that we are also making segmentation the architecture is to combine the global feature here, and also the per point features here in a way that we can also make some kind of layers of like processing each of the per point features like this. So this will be basically the architecture that you'll need to implement in the first assignment. And as I mentioned last time, I strongly recommend you to play with like all those kind of the parameters. Basically, we can change many kind of things, right? It doesn't need to be max pooling, like we can do many kind of things. And see how the performance is being changed every time when you tune each of the parameters. We're just talking some kind of some very basic ideas for the architectures, right? And last time we also discussed like why the point net would be robust to the many kind of the missing points. So last time we discussed the notion of the critical points. I'm not sure whether you remember those kind of things. So actually the quiz that we are going to take for today is that I'm going to ask like those things to you, whether you remember the meaning of that. So what was the meaning of the set of the critical points? And given a input point cloud, how do we tell whether each of the point in the input is a critical point or not? First question. And the second question is that when a new point is added to the input point cloud, does it necessarily like affect the global feature produced by the point net or not? if it affects the final the global feature, then how do you know whether that basically affects the final features or not? So please write down those kind of the questions, the answers, and please submit this to the KMS. So it's all because of the basically the max pooling here, right? Since we are taking the max pooling as our basically symmetric function, basically what we can see is that at this step, when you take the max pooling, basically for each of the dimension here in the global feature, the things that's gonna be happening here is that there will be like one of these the point out of all the points in the input, the point cloud, which is basically determining the number of each of the dimension, right? Which means that like there will be one single point here that contributes determining the number of each of the dimension. Which means that there can be some points that are basically deciding numbers here. There are some points that are basically not being selected as kind of the max number for any of the dimension. So the points that are basically choosing as kind of the max values for any of the dimension is the point that we call as the critical point. And those are basically only the points that determines the final, the global feature. Which means that even when you have some kind of the additional point that we are adding here, if that is basically not being selected at this step in terms of like choosing the max value here, that is basically not critical point, and then which is basically not affecting the final the global feature. So in terms of that, we can see which of the points are basically really contributing the final the results, and which are the points that are basically not making any kind of the changes in the final the point class. That also basically shows some kind of the robustness of the point net for many of the kind of the missing points. So even when you basically miss some of the points, if they are basically not any of the basically the critical points, then that will basically not change the global feature, and we are going to get the same results, right? So that's basically the basic idea that we are discussing here. Clear? So this was basically the things that we discussed last time. And we are going to continue discussing some kind of the some sort of the variants of the point net, or also the other the ideas of like making the point cloud encoder. And we're also going to discuss the point cloud decoder as well. So one quick thing that we are going to discuss here is that actually, while the point net is kind of the most the basic, while the effective the architecture to process the point cloud, like some of the limitations of the point net is that if we see the convolution of the neural net, which is the kind of most basic kind of things for the image processing, the basic idea of the convolutional neural net is that we are gradually increasing the receptive field in terms of that the features in the earlier stage become some kind of the containing the information in the local region, while as you basically increase the receptive field, we're gonna have some kind of features that basically covers the bigger region, right? So we are having this kind of the hierarchy of the features. The thing is that in the point net, there's no such kind of some deep hierarchy, only two levels, right? We only have the features for each of the single point, and at the end, we are just aggregating everything, making just like the global the feature. So only two steps. So here the question is that how we can basically also design this kind of the hierarchy of the features in a way that we can gradually basically increase the receptive field in terms of like having some kind of the hierarchy of the features. And also speaking to the transformation invariance, we discussed the rotation invariance last time, but how can you also design the neural net in a way that we can naturally achieve some kind of the translation the invariance? So the translation the invariance is also the feature that we can naturally achieve with the typical the convolution the neural net, right? You know the convolution neural net, right? So here the idea is that how we can also naturally basically guarantee this kind of the translation, the invariance in our the design of the point cloud the encoder. So those are kind of the basic things. So there's basically the idea that we are extending the point net into something that is called the point net the plus plus in terms of like making the point net to be get similar with a convolution neural net. So here the basic idea is that now we are performing the point net kind of the architecture not for the entire the points, but only for some kind of the local region. So based on that, we can basically achieve like all the properties of the computer neural net. The basic idea is that given a set of the points, we are going to take some kind of the key points like this. I mean, there are like bunch of the ways that we are making some kind of the key points. One of the simplest kind of the idea is the farthest point sampling. The basic idea is that it's basically incremental the way, like adding some kind of the key points. Given a kind of the k number of the key points, we can add the next key point by choosing the one which distance to the any of the key points, the closest distance to the any of the key points becomes farthest among all the remaining points. Make sense? So let's say this is somehow the first key point. Then what would be basically potential the next key point? You see something? This, yeah, or this, probably this one, right? So given this key point, we are basically computing distance from all the points to this single key point and choosing the one that becomes the farthest, probably like this one, right? Then after that, we are having this and this as the key point. And then now for any of the point, we basically compute distance to this and this and choose the minimum one. And among the, for all the points, we choose that the points which gives the farthest, the minimum point to any of like those key points. Then probably like this one or this one. And we can repeat this like multiple times in a way that we are having some kind of the k number of the key points. And based on that, like what we can do is that for the some fixed, some kind of the size of the some kind of sphere here, we take some kind of the local the point cloud here and performing the point net only for like this region. Make sense? And the way that we are achieving the translation, the invariance naturally in this case is that we are basically taking the local points here with the local coordinate system by just taking this seed point as the center, shifting all the points in a way that this becomes like 0, 0, 0, and then having this like local the set of the points and performing the point net. And then we can actually repeat this process. Actually, this is also kind of things that we are having the shared point net because we don't have the indexes here. So what you can do is that we have a one single point net that takes performs for this region and the other regions as well. And then the thing is that we can repeat this for the upper level as well. So now we are going to have a set of the key points for like those kind of the points, right? In the next layer, we see this set of the key points as kind of the another the point cloud. We can do the same thing. Given a set of the key points, we take another subset of the key points and perform the same thing. So that's the basic idea in terms of making some hierarchical the point set the features by repeating those kind of layers, doing some kind of the key point sampling and the grouping, performing the point net for the local regions, and repeat this kind of process in a way that the point becomes a just like single point at the end. Okay? Like very simple the extension that we are basically extending the point net into the some hierarchical way. And at the end, like if we have like the global feature for all the points, then we can simply perform the MLP at the end. How about the segmentation? Every time, like when you see some kind of encoder that takes some kind of the global feature, then we can also consider basically an encoder that takes also generate some kind of the per point feature, right? We can do the same thing that we have done for the point net case. There are also lots of the options for that. Like one simple the idea which was proposed by the point net plus plus is that we simply given any kind of the points in the higher the resolution, so the higher the density of the points here, in the previous layer, in this first the set of the points, we take some kind of the k closest seed point here, and basically aggregating all the features, taking some kind of the weighted sum of like those kind of features based on the distance, and just perform the NLP. So in this way, we can also do some kind of the sort of the deconvolution from the features, from this persist set of the points to the density the points of the set of the points here. So this is also kind of the simple the extension of the point net into the some hierarchical structure. So if you consider implementing this kind of the architecture, what would be some kind of the some component of the architecture that would be tricky when you use the PyTorch? Do you think that it would be quite natural to implement all the things you need in PyTorch? Can you see something like that would make you have some sort of headache in terms of like implementing things using the PyTorch? Now the first assignment does not include, as far as I know, implementing the point at the plus plus. But I also strongly recommend you to try to implement this architecture as well. This would be quite straightforward, extending the point net into the point net the plus plus. The only thing that I'm not sure whether the PyTorch now supports or not. It did not support, but probably some latest version might support. Is basically having this kind of the process in the point net. Basically, you need to basically take some kind of the farthest the point as the key points, and to need to basically take some kind of the points in the local region. Those kind of the process should be implemented in CUDA, or you might I don't know, the PyTorch might have some kind of the functions for those kind of things for now. This might be some kind of the non-trivial kind of a task in the neural network design. Other than that, everything else is kind of quite simple things, simply extending point net into the hierarchical structure. Clear? But do you also see what would be kind of the disadvantages like this architecture, especially compared to point net? It might basically involve some more competition the point net. Yeah, that's true. But actually, it's not making some kind of some very big competition the burden, because like the performing the point net here would be actually performing the point net for some kind of the local region. So basically, you can make the point net to be lighter. It doesn't need to have like all the layers there. You can make the smaller the point net, and also the number of the points for each of the region here would be way smaller. It also depends on how we choose the size of like this ball. It can be just take like just few hundreds of the points. Radius is not big enough, and some points was not like, wasn't it? Yeah, that's actually a good point. So actually, we need to carefully choose the size of like this ball, right? For some of the cases, the size might be too small, just having too few points. Actually, if the size like is basically becoming too small, then just takes like the seed point itself as kind of the input, right? Then actually we need to take at least like all the points as the key points, otherwise like we are losing some information. If we take some kind of the too big size of the ball here, that would basically result in like too much computation, right? With some lots of the overlaps of the points across all the kind of local regions. So we need to carefully choose the size of the ball. Typically, it's the hyperparameter, but we can also consider some kind of the mechanism that we automatically determines the size of the ball. Size of the current? Yes, we can see the kind of the analogy between the convolution the operation in the CNN, and also basically having some kind of the local the point net operation here. Yeah, that's correct. Any other questions? Why don't we choose some method that gives every point a certain neighborhood, like, I don't know, justify a box grid or use KD trees or whatever? So every point is included. You mean using the KD tree to define the neighborhood? Yeah. Okay. You mean effectively choosing the radius based on, yeah. But yeah, but Yeah, that's a really good point. I'm gonna get to that. Yeah, actually, my next slide is for that. So as kind of the advantage of the point net, like what we discussed is that even when you lose some of the points in the input, it does not affect that much for the final the outputs. But what we can typically see with the point net plus plus is that as we basically reduce the number of the points, you can see that the accuracy drops a lot, like this. Can you see why? The practical issues with the point net plus plus is that it's basically relying much more on some kind of the local region, basically how we define the ball, right? It should be the case that we are taking much smaller than number of the points. So for those kind of cases, when you lose some of the portion of the points, let's say like for the ball in the first layer, we only take like 128 points or like 64 points. And we are losing now like 20, 30 points out of the 128. That would be kind of like very big portion there, right? And then we also need to rely on some very small number of the points in that case. So because of those kind of the some like the architecture that we take some kind of point in the local region, as we basically reduce and miss lots of the points in the input, actually that affects a lot in the accuracy. Actually, this is really critical the points for many practical applications because especially like for the main kind of the applications of the point net might be just like processing some kind of the scan data. And for many of the scan data, actually the density of the points would not be uniform for many of the cases. The first reason for that is that naturally, if you shoot the ray along the direction like this, then as basically the points are basically closer, it becomes much easier to get some kind of denser points. But as you basically shoot the rays like farther to the long distance, then the points would become basically sparse like this. But not only because of that, because for the many reasons, because of some kind of the occlusion or many kind of things. We are also seeing some big occlusion here, right? For many of like those kind of reasons, there can be lots of the cases that the density of the points basically varies over the entire the space. So actually that involves some kind of problem. So if we basically choose the size of the ball based of the density, then that would result in the case that we are trained in neural net that basically learns from the density of the points, which means that at the test time, if you basically vary the density of the points, that will change the result. So if your application is really something that you need to train your neural net to learn from the density of the points, that might be a good option. But what I'm saying here is that for most of the cases, that may not be the case. We don't know what sort of variation of the density of the points that we're gonna get at the test time, depending on some kind of the angle that basically capturing the 3D information using the 3D scanner. The density of the points might vary every time when you basically scan again, right? Make sense? So this is kind of thing. We want to make some kind of the neural net architecture that is basically quite robust to the basically sampling density the changes. Whatever some kind of the variations of the density that we have, we want to get some kind of the similar the outputs. Make sense? Any questions? So that basically involves some kind of question. Then how should we basically design our some kind of the hierarchical the architecture of the point and the plus plus in a way that it becomes like more robust to this kind of the some sampling the density the changes. For that, actually, there are some kind of the bunch of some kind of practical the ideas. You can choose whatever you want to do. Like one simple the idea is that since we do not know what will be kind of the best the radius of the ball for each of the cases, we just choose multiple scales. Simplest idea, right? We choose like the small ball, like the larger ball like this, and for each of the balls, we just take some kind of the all different types of the features, right? Then depending on the situation, the neural net might rely more on some kind of the features of the smaller the scale of the ball, or might rely more on some kind of features coming from the larger scale of the balls. So this is really something that we can do. What would be the downside for this? Well, I mean, basically computationally expensive, right? We just need to perform the point net, in this case, like 3 times more. It was like just taking like one single scale. If we take the 3 scales, then we'd be just like taking the point net like 3 times more. It's like more computation. So if you are okay with like taking more computation, this is like one option.
Like take one radius and then we remove like every time there are too many points, you remove randomly some points.
Yeah, that's also kind of one thing that you can do. So we just take some kind of the bigger ball, and if we have like too many points, then we can sample some of them in a way that we have some like cap of the number of the points. But still, every time the problem is like, if we have some too few number of the points, that's the problem. So to avoid the situation that we are having the too few number of the points, then that would become the case that we are taking too bigger kind of scale of the points. Then that is not really just learning some kind of a hierarchy of the points. It's just like having just global the point, right? So lots of some kind of the options that we can consider, right? I mean, also another kind of the simple the idea is that now we are having some kind of the only 2 layers. So every time we are seeing some kind of a sparser set of the points, right? We have the original the point cloud here. Take some kind of a key point that becomes the next sparser set of the points. Putting the point here, or taking some key points here again, and making another dispersed set of the points, right? Having some the multiple layers here. Here the basic idea is that we are kind of combining the point net plus plus and the point net in terms of that for any of the layer, especially for some kind of the layer at the end, we are having like the point net, which is basically taking the points in the layer right before that, the previous this first set of the points. So this is basically the same way the typical the point net the plus plus, and the next layer is basically taking the points in the original the input point cloud. We only have the 2 layers of the points. In terms of that, we can still, so for the cases like the point cloud is like the 2 spurs, then we might rely more on basically some kind of the information coming from the input point cloud. For the cases that when you have some sufficient the density of the points, then we can rely more on some kind of some hierarchical pictures that we already computed from the previous 3 layers. So in terms of like having only the 2 layers, we can save the computation a little bit compared to the previous case. So these are some kind of the bunch of the ideas in terms of how we can make the point net the plus plus to be more robust to like missing the points. So those are basically the 2 cases that we are testing the 2 ideas. And you can see that now by just having some kind of the multiple the scales of the points, we can make the architecture to be more robust to the missing some of the points. So it would be interesting to see how much improvement that we can make using this kind of the idea. If you just try to do the first assignment, actually achieving the 90% with the model net, the TOEI data set, would not be that easy task. Actually, the 80 something was kind of some upper limit before we see the point net the plus plus. But with the point net the plus plus, now we can achieve some slightly higher, but exceeding the 90% with the more the computation. So those are some kind of the basic ideas with the point net the plus plus. Any questions? Yeah. So these are very basic the ideas, lots of the variance with the point net. So basically what we can think is that basically the point net the plus plus is the case that we are having the small the point net for each of the layer, right? So once we basically take any kind of the save point, it's like all the matter of like how we are going to aggregate information of the local region. Basically a set of the points in the local region, right? And we are doing the same thing. Basically, we make some kind of a symmetric function in a way that making this composition, somehow processing the neighbor points, aggregating all the neighbor point information using the symmetric function here, and having the analogy MFP here, right? And for that, actually, we are still just having the MFP here and also the max plane with the point net plus plus. But actually, obviously, there will be, in the history, there have been lots of people who tried like many different kind of options and just playing with that, what kind of the best way like handling those kind of things. Many kind of the variants, like one is basically taking some kind of the, still some kind of the NLP to get some kind of the per point features, but not taking the max plane, but doing some kind of the weighted sum. See? So this is basically some kind of the corner function and also the distance from the seed point, the center point to the all the neighborhood points, and we are taking the weighted sum, right? So there was really a case, not taking the max plane, but taking the weighted sum as kind of the another symmetric function. Yes. And actually, we also, someone briefly asked a question like about like, can you also use the graph neural net? Yes, we can use the graph neural net. And actually, if you see the architecture of the graph neural net, actually, you're gonna see that from the perspective of like making this symmetric function, the idea of the graph neural net is actually replacing the local point net into this way. Also, it's the case that we are having the two different kind of the NLP, extracting the features of the neighbor points and also the center point. And for the neighbor points, we are just taking the sum of the features. And at the end, we just do the perform the ReLU activation. So actually, this is the architecture of the graph neural net. You can see that what we are discussing is quite much related to the graph neural net. It's all the matter of like how we define the connectivity of the points, right? Makes sense? What else can you do? This is another kind of the variant, which is now not just taking the absolute the coordinates of the neighbor points, but take some kind of the more the relative coordinates. That's also what we typically do with the point at the plus plus, and also do the same thing, and also taking the max plane here. So this is also the basic idea, which is called the edge convolution. So what I'm saying here is that you can play with some kind of the loss of the variance of like this idea and see which one basically works the best. Make sense? And also one more thing in terms of like that we can change in the point net plus plus architecture is that, so we are also seeing some kind of the evolution of the points, set of the points, right? We have some input point cloud, take some kind of key points, that becomes the point cloud in the next layer. And also basically taking the key points again and doing those kind of things, right? And also what we can do is that we can also see those kind of like evolution in terms of that we are having the X, Y, Z coordinates and having some kind of the features for each of the points. And also we are repeating those kind of things. And when we take some kind of the neighbor points for each of the layer, we can also consider defining the neighbors, not in the 3D XYZ, the coordinate system, but taking the neighbors in the feature space. Is this clear? So what we discussed with the point at the plus plus is that every time we take some kind of the key points based on some kind of the distance, the farthest point sampling is all based on the distance, right? Based on the distance in the 3D space. We choose, given a set of the points, we choose the farthest one that becomes the next key point. And based on that, we also take the neighbor points based on the distance in that 3D space, right? That's basically what we discussed in the point at the plus plus. What I'm saying here is that since also we are going to learn some kind of the features in each of the layer, we can do those kind of the tasks, not based on the distance in that the XYZ coordinate system, but based on the distance in the feature space. Make sense? You know, the way that we hope the neural net is going to learn some kind of the feature space that is giving some kind of some better the notions of the neighbors of the points somehow in a way that gives some kind of the better results, right? So because if we take some kind of the ball in the 3D space, that is really just taking some kind of the neighbor points in that 3D space, right? But actually, we might actually want to basically process some points, not the neighbor in the notion of the distance in the 3D space, but the neighbor in the notion of the distance in the feature space. So that's another kind of some aspect that we can vary in the design of the point net encoder, point cloud encoder. So that's the basic idea of the dynamic graph CNN. So what they basically have done is that we are now taking the neighbor points not based on the distance of the Euclidean space, but in the feature space. So that can be also basically done in the space. The problem with this idea is that then this basically means that we should be able to basically find some kind of the neighbor points in that high dimensional space. If you took some algorithm course or something, that you're gonna see that actually finding some neighbors in the very high dimensional space is really time consuming thing. So sorry about that. So that's kind of the big issue. So if we start to basically find some kind of the features in the very high dimensional space, that actually will involve some loss of some kind of the computation. So that's kind of the big problem. But other than that, if you are okay with like taking lots of the computation, then you can go in this way. So lots of some kind of the results. So when you basically have those kind of the some dynamic, some kind of the graph in terms of the finding neighbors in the feature space, now we can achieve the even more the improvement going up all the way to the 93% with the model net. So actually, you can see this is kind of number that you can achieve in the first assignment if you do your best. So these are kind of thing. One more thing is that what should we do if we want to handle some kind of some deformable shapes? Let's say you have the human bodies or some, I don't know, some cats, whatever, some animals, like all the things. We want to classify whether this is the cat or the horse, like all the kind of things, right? You can see that for those kind of the deformable shapes, if you change the pose of the point cloud, you're gonna see that these all becomes completely different point clouds, right? Because we purely rely on the X, Y, Z coordinates. For the human beings, it's very natural to see that actually whatever we have some kind of some standing cat like this, or just like normal cat on the default pose, we see that these two are basically exactly the same thing, right? But since the information that we rely on in the point net the encoder is the XYZ coordinates, if we change the pose of the cats, those two different point clouds will be seen as kind of the completely different point clouds, right? Then the question is that how we can also make some kind of the point cloud encoder that becomes like robust to the changes of the pose for the deformable shapes. Like I'm not gonna get into too much details for that, but there are also some kind of the ideas that we can basically define some kind of the features. Sorry, someone is giving me some emergency call. Yeah. Sorry about it. So there are some of the ideas that we can basically compute some kind of the point features, which is basically based on kind of some intrinsic properties of the shapes. So we might have some time to discuss like those kind of things in terms of like how we can compute some kind of features for each of the point, which is basically quite robust to those kind of like the changes of the poses. So what I'm going to say here is that if we have those kind of some intrinsic features of the points that are basically not changing based on those kind of the points, the pose of the shapes, then actually we can start from this, right? We can consider those are basically something like kind of the learned features using the point and the plus plus. So not taking the X, Y, Z coordinates, but just directly taking these as kind of the input information in the point cloud, and then performing all the things in this feature space. And as I also mentioned, for the point at the plus plus case, we can also measure the distance in this feature space as well. So those are some also the idea that we can extend using the point at the plus plus for some kind of the deformability shapes.
So couldn't we use like the same idea to basically like change the finding
a deformation matrix and then apply it again to find like an intrinsic kind of shape and then go on.
Yeah, this is really good. Yeah, this is a really good question. So here the question is that as we also discuss some kind of the transformation, the invariance, and also making some kind of neural net that can predict some kind of the transformation, the matrix for some kind of canonicalization. Can you do the same thing for those kind of pose changes in terms of like somehow predicting some transformation, the matrix for those kind of the pose changes? Right? What do you think? This is a really good question.
With the approach, because I think how we understand that this is a horse and this is a horse is because we saw the horse moving in this way. And so if we input this into machine, that the horse can move this way, then it will be.
Yeah, that would be helpful. Any other opinions? Here that the biggest challenge is that how we are going to represent that deformation into a small matrix. That's the big challenge. Actually, we can get to that. I'm not sure whether we're going to have time to discuss those kind of ideas. There are very nice kind of the machinery in terms of how we can represent those kind of some deformation into some small, some compact form of the some either matrix or something. But typically, like it's basically not easy to represent those kind of some pose changes into the some compact form, into the some matrix form with some few number of the parameters. So that is actually a challenge. So if we do have any kind of the mechanism that we can represent those kind of the transformation into the some certain form of the matrix with some few number of the parameters there, then actually we can do the same thing. That's really the kind of key thing. But the problem is that how we can basically represent the transformation, the deformation basically into the form of the matrix. Lots of the questions here and lots of the interesting point. But yeah, we will see. Any other questions? Sorry. Yeah. And one more thing, obviously, we can apply the transformers as well. I mean, there are lots of some kind of the ideas, like what happens if we apply the transformer into the points. As I said, like one of the kind of the downside of the point net, the point cloud transformer might be is that it is basically taking lots of the computation, right? Especially like as we increase the number of the points, the complexity for each of the layer might be basically the n by n, involving lots of the computation. But other than that, actually applying the transformers into the point cloud is quite effective idea. So you're gonna see like how we can basically play with those kind of like just like the trade-off in terms of like the computation time and also the accuracy and what you're gonna choose depending on each of the application. So you can make lots of some decisions here. Okay. So if you're interested in some more advanced kind of techniques, I just put very few papers that are relevant to all the point cloud encoding. You can check out all those kind of things. Okay. So let me quickly move on to the point cloud decoder. So what we discussed before so far is all about basically how we are going to take point cloud as the input here and making some kind of some global feature or the PowerPoint feature. But now, so what we are going to discuss is basically how we are going to define some kind of the decoder as well. For many of the cases that when we want to do some kind of like 3D generation, so those are some kind of the earlier results of the 3D generation, making all the 3D things as kind of the output of the generated model. You can see for those kind of cases, we also need to have some kind of the decoder that can make some point cloud as the output. And lots of some applications like also taking a single image as the input and also making some kind of point cloud like this. So we can do those kind of things. And also for the cases like when you have like not the single image, but having the multi-view images like this, actually we can do something better. We're gonna get to this point. I guess some of you might already know the nerf, right? So we can also discuss the nerf later. But we are not gonna get into like too much details about the point cloud decoder. But the basic thing is that, so let's say somehow, yeah, before that, let's say, think about some kind of architecture that we are taking something as the input. Let's say here, like image as the input, having the image encoder from the global feature. We are going to make the point cloud decoder in a way that now we are having the n number of the points as the output. And we would need to basically compare this with some kind of the ground truth, the point cloud here, the desired output here. These are basically the given pairs, right? And then compare these two, define some kind of loss function, and perform the backpropagation, right? Here, the two main questions is that how we are going to define this architecture, and also how we are going to define this loss function, right? If we can do those two things, then we can just implement it now, right? What the idea for the point cloud decoder? Let's say we always want to make some like 1024 number of the points with the x, y, z coordinates. So having some kind of the global feature as the input, and the output becomes 2D array with the 1024 points and x, y, z coordinates for each of the point. Lots of ways for that, right? But we're gonna just like simply discuss like simplistic idea, like just like let's make some kind of the NLP architecture that just makes like 3 times like 1024 as the final the output of the NLP, and just like cut this into the 1/3 like this, and taking each of them as the x, y, z coordinates, right? A very simple idea. Actually, this works. Very simple idea. You don't need to take any kind of like fancy thing. This would be working for most of the cases. But depending on your applications, you can choose something more fancier things, right? Actually, the more interesting point might be is that how we are going to define the loss function here. Here's the thing is that, as I keep emphasizing, we are having a set of the points. The meaning of like having the set of the points is that there is no order. There is no specific way that we can say this is the first one, this is the second one. What if I change these two? Should be still the same thing, right? So we are having a set of the points here and set of the points here. And we are going to compare how close this one from this one. So it's the ultimate of like how we are going to define the loss function. How should we define the loss function in this case?
Not sure. Would it be possible to like transform point cloud to another vector perspective? Like use, I don't know, get a map and then
yeah. Here one point idea is basically converting this into another representation in a way that computing the distance from this to this becomes much easier, right? Yeah, we're gonna actually discuss like some implicit representation. Like with the implicit representation, like computing distance between these two would become much easier. The problem is that the conversion should be fast and also should be differentiable. That's the point. Actually, the conversion should be fast and also differentiable. We're gonna get to that. Actually, that's not that easy task. Right? Any other thoughts?
maybe we can make a pair between predictive point cloud and predictive point cloud and calculate that between those two.
Yeah. So somehow we would need to find a map from here to here, and then somehow measure the distance, right? That would be kind of the easiest way. So I'd like to actually introduce some kind of the 3 different ideas into like what people have tried to measure some kind of the discrepancy across the two between the 2 point clouds. The first one, which was actually introduced in the 19th century by the German mathematician, the Helix Hausdorff, in the 20th century, in the field of computational geometry, is basically defining distance in this way. Basically, the meaning of like this is that we see the worst case of the discrepancy. So what we do is that, so let's say X is like 1 point cloud, Y is another point cloud. For each of the points in the X, we find the closest one. For any of the points in the green points here, we find the closest one and check the maximum of the minimum distance. Make sense? For each of the point, we just find the closest one. If it's really close, same point, then distance is 0, right? It's good. Which means that that point has some kind of the partner in the other point cloud, right? So it's good. So we're gonna just check the worst case. What would be kind of the maximum from each of the point to any of the point in the other point cloud. What happens if you only have this one? Actually, yeah, that might be one of some questions that I might ask next time. So if we have like only one side, one way of the distance from one to the other point cloud, then that may not capture some kind of the discrepancy. So actually, we need to have the both ways. Also, for the point cloud, in the other point cloud, we also find the closest one and take the maximum. So the idea here is that we are just taking some kind of the worst case of some kind of like making the gap between these 2 point clouds. And the downside of like this idea, actually, this is really kind of the good metric that has been used in the many applications, especially in the computer graphics and the computer vision, to just really check some kind of some discrepancy between the two shapes. But the problem when you use those kind of some distance metric of the point cloud in the training of the point cloud decoder is that the practical reason issues using this as the loss function is that, which means that we are going to only take a single pair, the worst case, and only these points would be affected in the back propagation, which means that every step when you perform the gradient descent back propagation, only one point is updated. It's too slow. If you want to make some like 1024 points, every single back propagation is really just updating like a single point. That's not something that we want to see, right? It would be just two ways of the computation. So that's why we are also discussing something else, which is the Earth-Moose distance. Here, the idea is that now for the point in the point cloud to the X, we are finding some kind of the best mapping in terms of like minimizing the sum of the distance. So finding the best the pairs. When you assume that the number of the points is basically the same, basically finding the best one, the the pairs, in a way that the sum of distance becomes like minimized. And then we take this minimum sum of the distance as kind of the distance of the 2 point clouds. Make sense? Clear? So this is called the Earth-Moose distance. And the idea has been actually used many applications. So not only for the point cloud, actually the most basic kind of the application for this idea is when we want to compare some kind of the distribution. So let's say this is kind of some distribution for the multiple beans here, right? I mean the multiple beans, and we have this distribution and this distribution. So having the pair of the distribution here and the pair of the distribution here. Let's say this is kind of some sort of a histogram, I don't know, like some heights of the people in this room or something or whatever kind of thing, right? Having this distribution and this distribution and this one and this one. It all depends on how we define some kind of some similarity between the two distributions. But no, when you see this pair and this pair, which one looks more like similar than the other pair to your eyes? It all depends on how we define the similarity, right? But if we want to see the exact match, at least like this is the case that we are seeing the half of the match, right? Like at least like this one is basically the matching like this, while this one is completely different, right? But this one is not giving the perfect match, having some kind of the small shift into this direction. But some people might say, actually, isn't this like close to this than this? Because it's just like a simple shift along these directions, right? Makes sense? It all depends on how we define the similarity. But if we actually want to see that we have some kind of the tolerance about like making some small shift, but having some similar shape of the distribution is much more important than like just like having some perfect match like this. Then what we can do is that we can define the Earth-Moose distance in this way. So what we can do is that the minimum of the Earth-Moose distance is that how much kind of the move of the Earth you can see this collect this some kind of this some pile of some kind of the dirt. Like how much we need to really kind of like move some kind of some mass here in a way that we basically match the other one like this. So here basically the amount of the move that we need to make is basically not that big. You just need to move this one to this and move this one to this, right? While in this case, you need to make some kind of the much bigger the movement. You need to move this one into all the way to this region, right? So when you have the Earthmost distance as some kind of the measure of the similarity, you can see that actually this one becomes much closer than this one. Yeah, it's much smaller. The distance becomes smaller. So this is kind of the one of the idea in terms of like defining some kind of similarity metric. And the similarity idea can be basically used to measure the discrepancy between the 2 point clouds. Actually, there are lots of things that we can discuss here. I mean, because like we can also discuss the same thing, not for some kind of some math defined in the multiple the beans, but we can also define those kind of some metric similarly for the two probability distributions in a space. So when you have some kind of the probability distributions in the same space like this, how we are also going to define some kind of the similarity between the two probability distributions, right? For that, we can also extend the same idea in terms of like finding a joint distribution, which the marginal distribution matches the given the marginal the two distributions, while basically the weighted sum with some kind of the distance here becomes the minimized. So there are lots of the ideas in terms of like how we can utilize the same idea to define the similarity between the two any types of the distributions, whatever this is, discrete or continuous, like all the things. So let me skip some of the details here. But so it sounds like really good in terms of that we really find some kind of the best match and also basically minimizing the sum of the distance, right? What would be the downside for this? Yeah. Is any other thoughts? Basically expensive, right? We need to find the best match. Finding the best match is basically not the kind of easy task. If you took the algorithm course, you're gonna see that actually the complex of that, right? There might be some kind of more efficient algorithm for that, but actually finding the best match is just not that kind of the easy task. So that will actually involve some lots of the computation. If that is really kind of the efficient computation, then this might be kind of best way. The only problem with this is that it takes just more computation. So that's why like it all basically boils down to basically this simple idea, which is also called the chamfer distance, which is also introduced by the French mathematician in the 20th century, which is kind of relaxing some of like some properties of like those two distances in a way that kind of similar with the Hausdorff distance, but not taking the max, but just taking some. So when you see whether this is really kind of the good metric or good way to measure the similarity, this may not be the ideal way. Actually, this and this sounds like having some more, like some good meanings, like in terms of why we define the distance in that way, right? But why should you take this sum here? I don't know. It's just like one way to just define the similarity. So it does not have some kind of that, some kind of deep sort of the meaning in terms of why we need to define the distance in this way. The only advantage of like this kind of way of like defining the loss function in terms of training the decoder is that now we are just taking this sum, right? Which means that all the points in the output point cloud will be affected by the loss function. So this would not be the case that we are basically only updating a single point through the backpropagation. Like all the points will be affected by basically this kind of loss function. Actually, one kind of thing is that we're gonna actually discuss those kind of some practical ideas, not only for this, but many other kind of things in the next more basically the lectures. We're gonna see some interesting cases. Even we are breaking some sort of the physical rules, making something quite something heuristic, but actually turns out works the best in practice in many kind of reasons. And this is actually one of such kind of the case that while like these two distances might have some more meaning, this distance metric is basically effective in the neural net training and also quite efficient. Does not involve some huge computation. Lots of some kind of the ideas in terms of how we are going to define the loss function. So this also shows that the way that we define the loss function might need to be different with the way that we evaluate the quality of the outputs. We typically see that the way that we evaluate the final output actually should be used as some kind of the loss function in the training, right? For most of the cases, right? That's kind of the best way that we train our neural net. But for some of the cases, using the metric for the evaluation may not be the best way because of the fact that it might be too inefficient or it might just involve like too much kind of computation, right? For those kind of cases, we can consider using some kind of the good proxy function as the loss function in a way that we make the training to be more efficient. So based on that, we can do those kind of things, basically just taking the image as the input and making the point cloud as the output. And since we discussed the point cloud encoder as well, now we can have those kind of the architecture. So this is kind of the simplest way that we are having some kind of the point cloud autoencoder in a way that we are having the encoder giving us some kind of some compact latent representation of taking all the global information of the point cloud, and then basically having the decoder that can basically reproduce the input point cloud here through those kind of the autoencoding the architecture. So as you may know, some autoencoder for the images, now we can make some kind of the point cloud autoencoder as well. Okay. So actually the part of like implementing the decoder is not included in the first assignment. It was included before, but we just like omitted because to make it like simpler. But you can try yourself and see how much it works. Okay, so that's the end of the discussion with the point cloud encoder and the decoder. And before we wrap up today's lecture, one quick question is that how many of you are familiar with even heard about the quaternion? Oh, some people are you familiar? Yeah. So I guess 30 people. So since we also discussed the 3D rotations, I guess it might be also good to discuss some representations for the 3D rotations as well. So some of you might already know about some 3D rotation representations, but I'm going to quickly review those kind of the ideas next time. And after that, we're gonna move on to some another representation, the implicit representations. So I will see you next Monday.